In this video, we're going to learn about theories of acids and bases. Now, previously, we learned about the Arrhenius definition of an acid and base. Arrhenius bases will increase the concentration of H3O plus in solution, and bases will increase the concentration of OH minus in solution. The Bronsted-Lowry definition is a bit broader, and Lewis' definition is a bit broader still, and those two are the definitions that we're going to investigate in this video. So acids, according to the Bronsted-Lowry definition, they will donate an H+, and bases will accept an H+. So when we have an example of a reaction like this one here, which really is an equilibrium process, it very heavily favors the right, but let's call it an equilibrium process. The HCl, which you probably know by now is an acid, it will lose an H+, it will donate an H+ to the NH3, and that makes the HCl an acid and the NH3 a base. Now, NH4+ is the product of the base getting the extra H+, and so this one right here, NH4+, it actually will act as an acid itself. If this reaction is reversible, then on the right side, we need an acid and a base. And so NH4+ is going to be called our conjugate acid. So that Ca stands for conjugate acid. And the reason why we know this is the conjugate acid is that, well, NH4+, it's not going to pick up another H+ and become NH5 2+, but it can lose an H+ and go back to NH3. Also, our chloride is going to be the conjugate base because it doesn't have an H+ to lose. So it, on the other hand, can pick up an H+ from the NH4+, and go in reverse. And so this is a common way of looking at the Bronsted-Lowry definition. It's all about these acid-base conjugates and transferring H+ from one substance to another. And that's the conjugate acid-base concept. So a Bronsted-Lowry acid, that's an Arrhenius acid. Well, any Arrhenius acid is going to be a Bronsted-Lowry acid. And so let's take HCl or H2SO4, for example, or HCN. These are all cases where they'll act as Arrhenius acids, but they'll also act as Bronsted-Lowry acids. An example, though, of a Bronsted-Lowry acid that is not an Arrhenius acid is something like H2O. Now, H2O, you can't dissolve water in more water and have that increase the concentration of H3O+. Water is no more acidic than more water. And so here is a case, though, where you have something that is not an Arrhenius acid, but it can act as a Bronsted-Lowry acid. Bronsted-Lowry, we're really focusing more on scale. And so if you get something like water, which you don't typically think of as being particularly acidic, what if we put it in the presence of a very, very strong base? An example would be NH2- ions plus H2O. What's going to happen here is that our water will act as an acid, and the NH2- is an ultra strong base. And so we'll talk a little bit more about the strengths of acids and bases at a later time, and understanding that a little bit later. But if I were to show you this, you would have to label the water as the acid because we get hydroxide and NH3. Now, I know this process has increased the concentration of hydroxide in solution, but if you were to just dump water into more water, it wouldn't increase the hydroxide concentration. So here's a classic example of the breadth of Bronsted-Lowry acidity and basicity will come next. So an Arrhenius base, sodium hydroxide is a classic example that also will act as a Bronsted-Lowry base. But a Bronsted-Lowry base that was not an Arrhenius base, an example would be, again, we could say water, because water is not something that will increase the concentration of of OH minus in solution when you just add it to more water, but water can act as a Bronsted-Lowry base. And an example of that happening would be, if I move this over here, it would be where we have, say, HCl plus H2O yielding at equilibrium H3O plus, H3O plus Cl minus. So water is absolutely acting as a base here because it is accepting an H plus. And there are lots of possibilities here. We could go with even, I've actually seen nitric acid, HNO3, act as a base, and it would never, ever, ever act as a base. If you're just throwing it in water, it would be an acid, but I've seen it in the presence of a stronger acid. I've seen HNO3 act as a base. So the Bronsted-Lowry definition is just definitely broader, and it goes to the concept of scales. Everything's relative. Even an acid, most of the time an acid, can act as a base if it's thrown into something more acidic. Something else in this chapter, or this section of this chapter, is the concept of monoprotic versus polyprotic acids. Polyprotic, poly meaning many. So diprotic would mean giving up 2 H pluses, and triprotic meaning giving up 3 H pluses. This definition really just depends on how many H plus an acid can donate. So HCl has only 1 hydrogen that it can donate, so this would be monoprotic. H2SO4 is something that is diprotic because it gives up potentially 2 H pluses. And H3PO4 can be triprotic because it can give up 3 H pluses. And these are, by definition, the diprotic and triprotic, they can also be called polyprotic if you want to be a little bit more vague and not say exactly how protic they are. All right, so let's move on to the Lewis definition. The Lewis acid is something that will accept a pair of electrons, and Lewis base is something that will donate a pair of electrons. And when you think about it, if we've got a reaction between, say, we've got we've got an H3O plus, and that can react with an OH minus. Let's look at it like this. They'll form water, right? But we can say that the oxygen has a lone pair of electrons on it, and you can say that the lone pair of electrons can be used to pick up an H off of the H3O plus. In fact, if I really wanted to, I could draw out H3O plus as looking like this. And what happens is that the O will form a bond to the hydrogen, and that bond will break, where the bonding electrons go back to the oxygen, and we end up with 2 waters. And the waters are just H2O with our 2 lone pairs. So you can see how H3O plus, it needs to get a lone pair back. It gets it from those bonding electrons, and the O is bonding to the H. So everything ends up evening out here. But we have the acid being the acceptor of the electron pair. So our H3O plus is accepting electrons, and the donor of electrons is the OH minus. Now, all Arrhenius acids and all Bronsted-Lowry acids and bases are Lewis acids and bases. However, there are cases where there are Lewis bases Lewis acids that do not fit the Bronsted-Lowry definition. So, for example, a Lewis acid could be BF3, and you may recall BF3 as being a substance that is electron deficient because that boron does not have its octet. If you really count up all the electrons, the fluorines will be happy, but the boron won't. And so I could have, for example, NH3, which is something that can act as an Arrhenius acid, or an Arrhenius base or a Bronsted-Lowry base. But here it is acting as a Lewis base, and our Lewis acid will be the acceptor of the electrons from the nitrogen. So we end up with this complex N with 3 H's bonded to boron with 3 F's. And this is a very reasonable product to have, and it comes from B acting as a Lewis base, being something that is accepting an electron pair. Now, it's not just H3O plus or H2O that can accept the extra electrons. So, moving forward, we have these two graphics, which I think can be rather useful for your studies. We have the definitions, and you can see how broad, Arrhenius is very narrow, and Lewis is very broad, and Bronsted-Lowry is in the middle. I also like the way that this is presented, because with Arrhenius, we're just looking at something that increases the concentration of H plus or OH minus. With Bronsted-Lowry, it's not necessarily OH minus. We need to have something that can pick up an H plus. But with the Lewis definition, our bases, there can be a variety of bases. They will react with a variety of different acids. Bronsted-Lowry acids pretty much have to have the H plus, and Arrhenius definitely do as well. But notice how our definition broadens when we get to Lewis for acids, right? Because Lewis acids include more than just H plus. And Arrhenius bases, they have to be hydroxide, but Bronsted-Lowry and Lewis can be broader. They can be a variety of different substances. So I hope this video has been helpful. Let me know if you have any questions or comments in the comment section below. Thank you.